And yeah, so today, as I kind of promised you last time, today is probably what to me is the most meaningful of all of the things that I'm going to teach you. I mean, I did, I think, try to convey that local gauge invariance as the backbone of all of the standard model of forces was a really incredible symmetry principle that I really was amazed by the first time I saw it. But it doesn't tell the huge story like renormalization does. And so today we're going to finish our story on renormalization and see what it actually implies. And the breadth at which this is applicable is actually pretty amazing. So let me do a really quick review in a slightly different format of what we finished with last time, and then we'll move on to another, or we'll move on to its ramifications. So today's topic is, of course, infinity, okay? It's dealing with all the infinities that we encounter in quantum field theory, but we'll talk about other contexts at some point later. So one of the things that we've realized is that in calculating the amplitude m for a process, then typically the way that the amplitude m goes is that there's an overall delta function, which is what's governing the external momentum. And then, depending on the diagram, this isn't always true, but we can end up having to do an integral over some function of the external momenta, and then actually integrating over residual internal momenta that can't be handled with delta functions. Okay? So, do remember that if we do a tree diagram, then it turns out that the delta functions here, there are two delta functions, that's enough to completely evaluate the integral over that internal momentum. So that's not really a big deal. You have two delta functions. One of them you can use to evaluate this internal momentum integral, and then you get this delta function left over. However, as we experienced last time, here you have 1, 2, 3, 4 delta functions because you have 4 vertices, but you have 4 internal momenta, okay? So you can honestly see with the counting that there's no way you can get all of these momenta integrated over using delta functions. And then for higher order diagrams, that's obviously a continued problem, okay? And then of course recall that the divergences that we encounter in evaluating the amplitudes m tend to stem from the fact that the limits of integration here go from 0 to infinity. That's the weirdest looking infinity I've ever drawn in my entire life. That's not much better. Okay. Now last time I told you that one method of regularizing this is to replace the infinity up here with a cutoff. Just take the integral up to a certain value, and then you can carry around that cutoff throughout your calculation, and then you can relax it back to infinity. I'm just going to show you one more way to do this, and that is for each internal propagator, we can insert a factor of minus m twiddle squared c squared over qk squared minus m twiddle squared c squared, where the m twiddle is just a free parameter, okay? So this is just a number, it happens to be playing the role of a mass, but it's not in any way associated with the masses of any of the particles that are in the theory. And this is called a Pauli-Villars regulator. And one of the key things to first observe about it is that this is an innocent thing that you can plug into, into your expression, because if we take the limit that m twiddle goes to infinity, what does this become?
Infinity over infinity.
Which is?
1.
Yeah, well, I want to be careful because you said infinity over infinity, which is true, but, you know, what is this? Yeah, it's infinity squared over infinity, which is infinity over infinity, but does it give you 1 or does it give you infinity? You know, so what's important about this is that as m twiddle gets large, this term wins in the denominator, so we ignore that, and then that's genuinely 1, okay?
Yeah, sorry, I was a bit sloppy.
Yeah, well, I didn't hear you say anything, Ross. But that's okay. That's okay. Okay, so what did we discover? Well, first of all, we discover that m. Let me think about how I want to say this. If we're very lucky, then our amplitude m is going to break up into 2 pieces. Okay? One of which, and this is the entirety of our amplitude m, one of which depends on this mass, and one of which doesn't. This one, if we're lucky, is finite, even if m twiddle is taken to infinity, because it doesn't depend on m twiddle. Okay, so if this one is finite, then this one can diverge. And so what we've done is we've encoded the divergence of m in one term, and we've pieced off a finite contribution. So how many of you have ever seen this expression? How many of you have seen that? Okay, is that true?
Well, no.
No.
But actually, yes.
No, yes, kind of, sort of. What the hell does that mean?
Well, if you take the left-hand side and then subtract infinity from it, then it's correct.
Yeah, so the correct answer here is infinity, right? So this entire right side is infinity. But what this does is it lets us formally separate a divergent piece from a finite contribution, which is characteristic of this particular thing. So this allows us to, for example, calculate something like that, where naively looking at this, you'd say this is infinite, infinity minus infinity is 0, right? But what if these have finite pieces? And then you can just say, oh, okay, this is minus 1/12 plus infinity, plug it in here, and then you get a finite difference, okay, which is not 0. So this is the process of regularization in numbers, and the process of regularization in the matrix amplitudes roughly corresponds to this. We get a divergent contribution, and then we get a finite contribution. And then what's nice is the following. If the m twiddle dependence in the divergent contribution can be encoded in parameters like the following. Then what we can argue is the following. in our calculation, we assumed that these values, which last time I defined as the bare values, that these values took a finite, value, that maybe they were the ones that we look up in books, okay? So you fix these at some finite value, and then these things are shooting off to infinity, therefore these things are shooting off to infinity, okay? But we realize, no, actually, these are the things that we actually measure. So these are the physical values of quantities. These are the things that we measure at, for simplicity, zero momentum transfer. If these are diverging, then these quantities, which are the bare, they are the naked, completely nude values of the mass and the coupling, which are pieces of information that we have no access to, then these things could actually be diverging in exactly the manner necessary to cancel off the infinities that are arising here, leave a finite piece which corresponds to the physical values. Okay? So what we discover is, if the infinite divergence in the matrix amplitude can be encoded entirely within these redefinitions of the parameters of the theory, and this is the notion of regularization, by the way. It's rendering the thing finite because we got everything with m twiddle, but ultimately we have to take m twiddle to infinity and let the infinities come back. But if we can make this argument and handle all of the infinities that happen in m, then m is called renormalizable. Okay, so there's two steps to the process of renormalization. There's regularization, which is writing it in a finite manner, where you can still take whatever the parameter it is to infinity and restore the infinities. Examine how parameters are broken up into divergent and finite pieces. Okay, and then by interpretation of physical versus bare quantities, as long as you can handle all the infinities that arise in your matrix amplitude, then your theory is renormalizable. If you have more infinities here than you have parameters to redefine, then your theory is non-renormalizable. Okay, and that can happen. In fact, I'll give you an example of each. The standard model, that is electromagnetism, or electroweak gauge theory actually, quantum chromodynamics, QCD. This is renormalizable. Okay, this was demonstrated by Gerard de Hooft back in the 70s, which was a highly non-trivial exercise. Anybody know what that stands for?
Quantum gravity.
That's quantum gravity. Okay? Quantum gravity, when I use these words, and I'll come back to this towards the end of the lecture, quantum gravity is essentially treating gravity with the tools of quantum field theory, because what you can do is you can say, okay, I'm going to take space-time to overall be flat, and then I'm just going to analyze small curvature fluctuations. And then I can use perturbation theory, I can use Feynman diagrams and so forth for how these little ripples in space-time interact with each other. This is quantum gravity. This is applying perturbative quantum field theory to gravity. This theory has infinities in the amplitudes that can't be handled through the redefinitions of parameters. Okay, so quantum gravity is a non-renormalizable theory, and we'll come back to the interpretation of that at the end. Okay, so there is that's a rough review of the process of regularization and renormalization, and what we really want to do today is take that somewhere. But beforehand, I gotta clarify something that we talked about last time. So last time when we were talking about doing electron-muon scattering, then we really only wanted to focus on this fourth order diagram. Okay? But there are other fourth order diagrams that contribute. For example, we have fourth order diagrams like this. Fourth order diagrams like this. Fourth order diagrams like this. Plus, we come down here. Okay? Now my argument to you last time was that this was the only fourth order diagram that we really had to worry about. Okay? Well, first and foremost, one of the things you have to remember is that in the program of renormalization, there's two important consequences. One is we can take the exchanged momentum to infinity, or sorry, we can take the integrated over momentum to the integrated over momentum. Yeah, that's what I want to say. The momentum that we're integrating over to infinity, and that can cause M to diverge. But even if you don't have M diverging, you find that you can completely encapsulate M in this diagram if you use couplings which are defined at the scale at which momentum is being exchanged. Okay? So this gives rise to what we call the running couplings or the running masses, the running parameters in general. Now it turns out that things can run even if they're not going to run to infinity. And what we discover is that these three diagrams have very interesting impacts. This one, or these two, correspond to self-energy corrections of the electron. I could have drawn these three loops on the bottom as well, and then in that case it would have corresponded to the same shift in the muons, but I'm just doing the electrons as an example. So these give rise to self-energy corrections to the electron, which basically corresponds to shifts in its mass. So this is what gives rise to the mass, the momentum dependence of the mass of the electron. And this gives rise to a correction to the magnetic moment of the electron. Okay? Now, all three of these together, though, all three of these together give rise to electric charge renormalization. Okay, so each of these contributes to electron charge renormalization. However, all three contributions cancel. So if your focus is on the renormalization of the electric charge, this gives you an infinity. These three cancel. These two are finite. Okay? Now, that's not really a big deal because, you know, if these were divergent, then, you know, we could probably renormalize the theory by redefining, you know, other stuff so that, you know, all this would work out. We could redefine the masses, etc., etc. But there's a problem with this, actually. And that is that these diagrams are contributing to the renormalization of the mass of the electron. They're also contributing to the electron charge renormalization, which means if these did not cancel, then the electron charge renormalization, that is, how does the electron charge vary with q squared, would actually depend on the mass of the electron. Okay? Which you might say, who cares? You know, the mass of the electron can contribute to the electron charge renormalization. Right? Make sense? Except for the following. Remember, we can do it to the muon as well. If you do it to the muon, then the muon's charge renormalization is going to depend on the muon mass. Does that seem so bad? What is bad about that?
Well, we don't observe them to have different charges.
Exactly. We observe the electron and the muon and the tauon to have identically the same charges. But if their renormalization was dependent on their separate masses, well, their separate masses are hugely different. Okay? So that's the miracle that occurs in the cancellation of these three diagrams. Okay, so what I'm going to do now is I'm going to move to QCD, and I'm going to work on this particular example for a moment, partly because this gives us an insightful answer. And all I'm going to do is I'm going to talk about charge coupling in QCD. So, whoops. All right. So let me start by making the following observation. Okay. So first of all, in QED, this guy had a tree level contribution plus a one loop contribution that we have to consider if we want to consider the renormalization of the charge. And last time we said that, let me see, alpha squared. Yeah, I'm going to write this in terms of alpha. So GE is square root of 4 pi times alpha E. So I'm going to write this in terms of alpha instead of GE. But alpha q squared could be defined in terms of the zero momentum transfer value of the parameter times, and this should be familiar to you, okay? Now, it turns out that if you would like to do this to all orders, then the result is actually analytic, okay? So the result actually ends up being of this form. Okay? So yeah, don't worry about why, but I just want to show you you can get the first two contributions, or you can actually do all infinity contributions. Okay, and you might guess that there's sort of a pattern because the only diagrams you're allowing are these bubbles. Okay, now. What does this do as we increase Q? goes up, right? So this increases with Q squared, which leads to our interpretation of this in terms of screening or anti-screening. You remember the screening and screening part of the story? Say it again.
Anti-screening.
No, it's screening. Because as we probe the system with larger Q, that means we're actually going to get closer to the fundamental thing, which in this case is the muon. As we go with larger Q, larger momentum, larger energy, whatever you want to call it, that's a smaller distance. We're experiencing a larger coupling, which means that the coupling is being screened by these external particles. So the closer you get, the larger the value of the coupling. Do you remember this from our discussion on Tuesday?
Yeah, sorry, I just made a mistake.
That's fine, okay. What about this one? What happens to this one as Q gets bigger? Do you see where Q is in here?
It gets smaller.
Q is right there.
I think it'll get bigger because, like, as Q gets bigger, then the natural log gets bigger, and the denominator gets smaller, and so the whole expression gets bigger.
Well, wait, but wouldn't the denominator go to like negative infinity?
You tell me.
That natural log term would dominate.
Who says this gets bigger? Raise your hand.
I mean, it probably should, but like.
And who says it gets smaller? Raise your hand.
Well, it looks like it gets smaller.
It should go to 0, right? Because it's 1 minus the natural
Are you
log
asking-
squared.
Are you talking about the
Like, is it
denominator?
the bottom part or the whole
I'm asking for the whole thing. Is the whole thing getting bigger? Raise your hand. Is the whole thing getting smaller? Raise your hand. Okay, let me see the biggers one more time. The yellow thumbs up or is remaining up? Okay. Well, let me ask you a question. So we're talking about dialing Q. That's the momentum transferred. Where should we start the dial?
Zero.
0. We should start it at 0. That is, we're barely throwing the thing in there. In fact, 0 is important because 0, of course, tells me that this is equal to alpha 0. That corresponds to our physically measured values. Okay? So now as we start increasing Q from 0, this is going to grow until eventually it's equal to 1. And when it's equal to 1, what have we got?
Something over infinity?
No, we've got something over 0, which is an infinite. Beyond that, this starts getting smaller. But it's not like you can ignore that infinity. In fact, that infinity occurs at a finite value of Q. It turns out that when Q gets to the order of 10 to the 280 MeV, that's when this thing actually becomes infinite. Okay? All right? So we still have the renormalizability problems, but what I wanted you to see is that this is increasing with Q, and this is increasing with Q to infinity, and then it's decreasing, but I don't think we need to worry about what happens past infinity. Okay, because once we hit infinity, the theory's screwed up. So this also increases with Q squared. Okay? And so this also describes screening, which was kind of what we would have expected. We would have expected that if this first order correction gives us screening, then these should also give us screening. Because, right, these are just acting like polar atoms or polar molecules or whatever, and those are just going to screen, okay? Now, I want you to consider, instead of QED and electromagnetism, I would rather you consider QCD. Okay? For QCD, it turns out that a very similar story plays itself out. You can have this tree level diagram and then these loop corrections, okay? And these all lead to screening effects, okay? However, are there other diagrams that we should include in QCD? Are there other vertices that we can use?
3 gluon and 4 gluon vertices?
Yeah, remember QCD has interactions with the gluons. So it turns out that in addition, you can have a fourth order diagram that looks like that with an internal gluon loop. That's using the 3 gluon vertex. Or you can use the 4 gluon vertex, etc., etc. Okay? Well, it's not clear what these are going to do compared to these, and we're not going to go through the calculation by any stretch of the imagination, but all I'm going to tell you is that these diagrams contribute anti-screening. To the coupling. Okay, so now I'm talking about alpha S. Okay, this is the strong interaction coupling. That is, as we increase the energy of the incoming quarks, we find that the contributions from these diagrams are actually getting smaller. So these are getting bigger as usual, but these are getting smaller. So in QCD, we have both screening and anti-screening. And this can be at the same order. This is a fourth order diagram. This is a fourth order diagram. It's actually a third order diagram, but it's got a quartic interaction. Okay? So the big question is, which one wins? What do you think? Well, it depends. It depends on 2 numbers. It depends on the number F, which is the number of flavors, and it depends on the number N, which is the number of colors. Now, I'm being very generic right now. We can pin down these numbers in just a minute. But what we discover is that alpha S, as a function of Q squared, takes the following form. Where mu squared, I will discuss in just a moment. Okay? All right. Does anybody notice that factor right there? 11n minus 2f. This is the result of evaluating all these diagrams, and they're actually all evaluated to infinity. But in this final expression, you have a factor of 11n minus 2f. Okay? What can you tell me about the screening versus anti-screening? Whoops. When 11... Good God. 11n minus 2f is less than 0. Does this correspond to overall? And this includes both the screening and the anti-screening parts. If 11n minus 2f is less than 0, which wins, the screening or the anti-screening? The screening, right, because if this is negative, then that changes this to a negative, which is basically the result here. Okay? So here we have screening. Which of course means if it's larger than 0, then anti-screening wins.
What if it is 0?
It won't matter. Because after all, we have the standard model, right? We know what N and F are. What are N and F? How many flavors of quarks are there? Remember,
6 flavors.
it's 6. The flavors are the different names of quarks, and there are 6 different quarks, up, down, charm, strange, top, bottom. So F is 6. What is N? 3. So for QCD, it turns out that anti-screening wins. This has a profound implication, because imagine this. If I take 2 quarks and put them very close together, and close together is synonymous with large energies. To get things really close together at really small distances, you have to use a lot of energy. But when 2 quarks are at a really small distance, their coupling becomes small. In fact, you can take the limit. If their separation goes to 0, then their coupling goes to 0 as well. Okay? This is a phenomenon that's called asymptotic freedom. And this is actually a key in the ability to use perturbation theory to look at processes like scattering of baryons. Because the baryons are systems of 3 quarks, and we talk about this baryon interacting with this baryon by the exchange of a gluon between 2 of the quarks. But at the same time, we don't really worry about all of the gluonic interactions that are happening between the different quarks in this diagram. And it turns out that we don't need to, because the 3 quarks that are bound in a baryon are so close together that effectively their coupling is 0. Okay, so we can ignore their mutual interactions. Now, the asymptotic freedom tells us, why we can use perturbation theory to deal with this. However, if we flip the argument on its head, then it might actually solve a problem that I talked about when I talked about QCD, and that is the following. If 2 quarks are very close together, their coupling is marginally small, but if I then separate them to some large distance, that is, I separate them to a lower energy interaction, what do you think is going to happen to the coupling?
It's going to go up.
It's going to go up, yeah. So what we have is that if the things are close, their interaction is minimal. The further we pull them apart, the stronger their interaction becomes. God damn, that reminds me of something. What do I need? Hold on.
A rubber band?
Nothing. Oh my God! It just gets stronger and stronger.
Is that what rubber bands sound like?
Yes! That's the rubber band talking, not me. That's the rubber band talking, not me. Okay, no, seriously. This seems to completely make sense, not just asymptotic freedom, but also confinement. And by the way, me and the rubber band, that might or might not remind you that this was the motivation for studying string theory. Thank you, Hunter. I appreciate the rubber bands. So the study of the band structure was actually what was the seed of string theory research. But here, what we've just proven, because the coupling grows at larger distance and it's small at smaller distance, that explains why you can't pull quarks apart, right? Does this make sense? No, it's fucking wrong. Why is it wrong? What's wrong with it? What's wrong with this? What method of analysis are we using here?
Perturbation theory?
Yes. Here the coupling is getting larger and larger and larger. Eventually it will pass the value of 1, in which case perturbation theory will no longer apply. Joseph Joestar. Okay, I'll read your chat comments later. Okay, so yeah, we have to remember that if we're using perturbation theory to make an argument, but the parameters describing that argument go well outside of the bounds of perturbation theory, then we can't say that the conclusion that we reached using perturbation theory holds. This is, of course, why asymptotic freedom is an accepted conclusion of perturbation theory, but its argument for confinement is not, and in fact, we still don't have a resolution to the confinement argument. And if you can come up with a good one, you can get the Nobel Prize. Okay? Good. All right, so now we're going to see where this all goes. So that was just a look at the QCD situation to see where you can have competitive effects, and then obviously one of them wins in the standard model. Now it's time to really get down to earth and talk about what the hell does all this mean. Okay? So I am going to throw a historical anecdote at you. So back in the day, a beta decay process, which is a neutron decaying into a proton plus an electron plus an anti-electron neutrino, this was analyzed using quantum field theory, but the first diagrams that were drawn to use perturbation theory to analyze it were actually these. So this is the first tree level diagram that was drawn. Okay? Now, if you look at this, I will ask you, does this actually arise in the standard model? Four matter particles all meeting at a point. No, if you review all of the diagrams that I had given you in, Feynman rules for the electromagnetic, the weak, and the strong interactions, none of them involved 4 particles meeting. It was always particles and gauge particles, or gauge particles and gauge particles, okay? But this is what Fermi considered, and it turns out that his calculation largely gave him the correct answer, okay? It largely gave him the correct answer for the magnitude of the momentum being exchanged small enough. Okay? Well, eventually, at large enough values of momentum exchange, at high enough energy experiments, comparing this calculation to the results met a disagreement. And of course, eventually, the picture was more cleanly, we can say cleanly, the picture was more cleanly developed to look like this. Actually, Okay? Now, so it turns out that if you go to large enough q squareds, then this diagram actually gives you a more correct answer than this one. All right? Now, something that was noted is when they did this calculation, they discovered that it was non-renormalizable with q squared approaching what value? Well, actually, I'll just call it a number x. I'll tell you what x is in just a moment. Okay? So in this case, the contribution is renormalizable. And so what we want to do is we want to understand the difference between this diagram and this diagram. Well, if we actually write down the amplitudes for these two things, well, they're not that bad. So for this diagram, I'm going to write this one on top. We have U bar for the neutron, and I'm just going to treat these as one particle. So this is the neutron and this is the proton. We have U bar for the neutron, gamma mu, 1 minus gamma 5, U for the proton, minus I eta mu nu, minus Q mu, Q nu, over mw squared c squared, over q squared minus mw squared c squared, times v bar for the neutrino, gamma nu, 1 minus gamma 5, times u for the electron. Okay, so that corresponds to this diagram. For this diagram, if you work out m, you end up with an expression like the following. So most of it is the same, but the vertex factor is different. Okay. Now let's make sure that these two results for M make sense. For this diagram, we basically have the spinor sandwich, which is associated with following the neutron end. There's a vertex factor, and then we have the neutron in, the vertex factor gamma mu, and then we have the proton going out. We have the propagator describing the W minus, okay? And then we have the spinor sandwich corresponding to the neutrino coming in, the electron going out. Here, we have the spinor sandwich of the neutron and the proton, the spinor sandwich of the neutron and the proton, and then we have a spinor sandwich of the electron and the neutrino. And this factor is not really a propagator. Okay, this is more like a contribution to a vertex factor, if you will. Okay? Huh. Well, that's interesting. Well, let me ask you a question. What does this become as long as Q is much less than the mass, than this massive particle times c. If the value of the momentum that is exchanged is much smaller than mw times c, where the mass that I'm talking about is actually the mass of this weak gauge boson. But if q is much smaller than mwc, well, this goes to 0. This is smaller. Holy shit. So if q is much smaller than mwc, this reduces to this expression. Okay? So what we find is that for momentum exchange much smaller than the mass of this thing, we can effectively replace this picture by this picture. Now there's an important observation. This picture is much easier to work with than this one, right? Okay, there's no Q left in here. All right? But this theory predicts its own demise, because as the momentum transfer gets close to the scale MWC, this thing is going to diverge, and that's going to eventually lead you to needing this theory. So this is the idea of the following. And this is due to Kenneth Wilson in the 70s. So I told you last time, Kenneth Wilson is the guy who came along and he looked at all of these renormalization and infinity stories and everything, and he was like, you know what? This is, I think, what's going on. Okay? If we have a non-renormalizable theory with a cutoff of its validity. In this case, we had a non-renormalizable theory, and we knew that you could use this example until Q got close to MWC, but when Q got close to MWC, this just went to shit, and you had to move up to this theory. Then beyond the cutoff to the theory, which is this value, we must turn to an ultraviolet completion. That is, if we're starting at low energies and we have a description which is working, and that description starts to fail at a certain energy scale, or momentum scale, pick your poison, then our expectation should be not that this theory is fundamentally sick and should just be thrown in the garbage. It's that we can use this theory as long as we haven't reached this scale, but for processes at this scale or higher, there should be a replacement theory, a theory that will give you an answer, a more accurate answer, possibly a finite answer. And that completion is the ultraviolet completion. Ultraviolet because it's higher energy. Okay? Now we can turn this around. And we can make the following argument. We could say, if I have a theory which is good at all energy scales, but I consider processes where the energy scale is much lower than the energy scale associated with some aspect of the process. In this case, we can compare it to the mass of W. Okay? So I could take this description, and as long as the energies that are being exchanged are much smaller than W, still larger than the energies of the the proton, the neutron, the electron, neutrino. But as long as the energies are smaller than this, I can replace this description with this. That's called integrating out the massive degrees of freedom. Does this make sense? I mean, look, all I'm saying is you have this correct description, but as long as you're working with an energy scale smaller than this, then you can reduce it to this one. That's basically taking this guy and it's going down here. Which, don't get me wrong, this is a constant, but a constant isn't bothering anything. It's really the integration over these momenta disappearing, which is the canonical factor. Okay? So there's two directions. One is starting with a more realistic, more comprehensive version of the theory at high energies, that's valid at high energies, and to go down to simpler versions of the theory that are valid at low energies. We integrate out the high energy degrees of freedom. These are the more massive particles. Okay? This is, of course, why, you could do QED. So they could do QED processes and discover pretty much the right answer, even though this is a possible contribution to electron-electron scattering. This is a W plus W minus virtual pair. But these masses are so big that at low energies, this diagram barely contributes at all. So if we start with a more complete description and we go to lower energies and we get to energies which are below a certain scale of a fundamental parameter in the problem, like a mass term, then we can integrate out those massive or high energy degrees of freedom. And normally this ends up with a reduction in the degrees of freedom. Okay? Alternatively though, if we start out with a theory at low energies, and that theory is not, applicable to infinite energies, then what we would first of all realize is that it's non-renormalizable, and that there's some cutoff beyond which we have to replace the theory with the more fundamental description. Now, what I am talking about here is replacing this quantum field theory with this quantum field theory at high energies. But that's by no means the only means in which we have to do this. For example, I can take a discrete system Okay, so this is a discrete atomic system. And as long as I look at length scales, which are much, much larger than the separation, then I could likely replace this by some continuum theory. Maybe it's a field theory. Okay? I mean, isn't this how we think of water, right? You know, water we think of as a continuous fluid, but is water a continuous fluid? No, it's a bunch of H2O molecules. Okay? So we can have a continuum theory description of a discrete system, but what you will find is that this continuum theory is non-renormalizable, and what emerges from it, if you study it, is the cutoff beyond which you cannot use the continuum approach anymore. But the cutoff for this is exactly this length here. Because if you take the distances over which you're considering this and you shrink them down and you get anywhere near the actual distance between the molecules or atoms, clearly your continuous description is going to break down. Does this make sense? So I don't want you to think that renormalization and the replacement of a theory by an approximation is something only relegated to quantum field theory. This is true throughout all of physics. Okay? All right. So we're going to end with quantum gravity. because after all, the standard model was renormalizable, but gravity is not. Now remember, to find the sickness of gravity, then the fact that it's non-renormalizable, we have to use this perturbative approach. So again, we're thinking of space-time as largely flat, and then we're just looking at small fluctuations, and we're treating those perturbatively, but the perturbative treatment using Feynman diagrams, because you're quantizing this, the perturbative treatment of that leads to non-renormalizability. But based on what I just said, this being non-renormalizable should have a scale up to which using quantum gravity is fine. And I want to reiterate, just because a theory is renormalizable doesn't mean it's not useful. It's useful as long as the momentum exchanges and so forth give you a are well below the cutoff. Okay? But often the theory carries around in its workings the cutoff. Okay? So quantum gravity is very useful up to a certain scale, but beyond that scale, we would expect there to be some ultraviolet completion, some more accurate quantum version of gravity. First of all, what is that scale? Well, you know, if you're doing gravity and you want to find the scale, because you don't have to include the standard model in this. I mean, quantum gravity is just like literally a particle of mass. Fuck its charge, fuck its spin, fuck all that. You know, it's just like literally just energy and mass and all that stuff. So if you want to try and extract a numerical quantity for the upper limit at which this theory is valid, nice, Avery. Then you have to take whatever parameters lie in your theory. Well, what parameters do you think? What like physical constants? Remember that we're not including the electron, so the electron mass can't be part of the answer. Neither can the proton mass or the electric charge or anything like that. What parameters do you think we could actually cobble together to get the point at which this theory needs to be replaced by its ultraviolet completion? What do you think we can use?
Newton's gravity constant, maybe?
Anything else? You better. The speed of light.
H-bar?
Yes. If you didn't have all three of those, you'd be screwed because you couldn't get the units to disappear. Okay? But yeah, these are the three fundamental constants, okay, which are part of a quantum gravity theory. Remember, we've got a quantum in there, so h bar actually plays a role. Otherwise, it would have just been G and C in classical general relativity. So we can take these and we can extract several different limits. We can talk about a mass limit, in which case we do root h bar c over g. This turns out to be 10 to the minus 8 kilograms. We can do an energy scale, which is just the mass scale times c squared, which gives me 10 to the 19 GeV. And L Planck, which is root h bar g over c cubed, which is 10 to the minus 35 meters. Okay? That's not that big. 10 to the minus 8 kilograms. That's not that big at all. But I want you to remember, we're not doing classical general relativity here where we argue, oh, you got to use big objects like planets and stars, which obviously have a hell lot bigger thing than that. We're trying to do perturbation theory. We're trying to do a version of general relativity where the quantum effects are important. Okay? So the quantum version of general relativity, quantum gravity, seems to have this upper cutoff, which is 10 to the minus 8 kilograms. This is the range beyond which you don't think this is going to be applicable. But just to give you an idea, the largest mass scales we have ever encountered in the standard model are either the weak scales or the Higgs scale. Those are both at about the same range. And those scales are 10 to the minus 25 kilograms. So this is actually a hella large number. Okay? Way, way, way bigger than this. Way bigger. So what I'm saying is that this description of quantum gravity can actually be taken up to extremely high energies. But there's a point, either in terms of the mass, the energy, or the length. There's a point at which we know that at that energy level or length scale, that theory is going to break down and has to be replaced by its ultraviolet completion. Now let me ask you, are there situations in our universe where you expect things to reach those energies?
Black holes?
Yes. Anything else?
I don't know, like quasars or some shit.
The Big Bang. Okay? Those are both situations where the energy density is so incredibly, I mean, you take the entire universe and put it in a point. That's got a pretty high energy density. Or you could just take a star and put it in a point. Okay? So these enormous energy, look, if there was no way to reach these energies, then maybe you don't have to ultravioletly complete this. I mean, if this scale is so large that nothing in this universe can even conceptually, theoretically reach it, then maybe it doesn't matter. But it turns out that in the interior of black holes, near the singularity or near the singularity of the Big Bang, you are well above these scales. So there has to be a replacement theory. Okay? Now there are roughly two categories of replacements. The first one is loop quantum gravity. Loop quantum gravity is essentially a generalization of GR. So what loop quantum gravity does is it takes general relativity and it modifies it just a little bit. And I'm not by any means an expert in loop quantum gravity, but I do know this. It starts out with GR and changes it a bit to render it finite, so that you don't have this, I should say something which I don't think I've said, but I want to be clear. So if you start out at the lower level, you have a non-renormalizable theory. And then you flow to high energies or mass scales or small distances or whatever, and the UV completion must be either renormalizable or finite. Okay, so the non-renormalization or the non-renormalizability of a theory is what's pointing to, oh wow, at a certain point the infinities are unavoidable. However, if the theory is completely renormalizable, then that means that the infinities which you see, you can always remove by saying, I don't know the actual bare values of things. I just know the physically measured values of things. So the standard model doesn't face this problem. The standard model in principle is accurate up to infinite energy scales. It's gravity that predicts this energy scale beyond which it has to be replaced. Okay? So at the high level of replacing the non-renormalizable theory with the UV complete theory, you can either get a renormalizable theory, or it can be finite. Okay, that is, there's no infinities at all. You just calculate diagrams and everything is finite. Okay? Loop quantum gravity basically gives rise to a renormalizable form of gravity as the ultraviolet completion. All right? And, you know, the replacement is they're replacing the field theory of gravity with this gravity where the degrees of freedom are these loops, and I've always hated it, so I can't really explain it to you. But what's important, and I want to reiterate this, what's important is that all they're doing is they're replacing gravity with a new version. The standard model still goes along as a field theory, okay? And they get a renormalizable version of the ultraviolet completion, and you know that might be the way the universe works, except for string theory, which is better. In string theory, this does not take gravity and try and generalize it or change it or modify it. That's not the way string theory was born. String theory takes point particles and makes them into strings. Remember, it was accidental that we discovered it because we were trying to explain the confinement by saying, you know, these things are connected by some flux tube, and analyzing the dynamics of the flux tube at the QCD scale eventually led to all these problems, which they realized, wow, if we take it down to the Planck scale, then those problems, and they solved some of those problems, but one of the major problems that they discovered was that band between the two, objects was giving rise to spin 2 fluctuations, which actually correspond to gravitons. So string theory starts out as a change of point particles to strings, and in doing so, it gives you some really nice consequences. First of all, string theory actually gives you a finite quantum gravity theory. Not a renormalizable one, but it's actually finite. And the reason for that is simple. Where were our infinities coming from in our perturbation diagrams and so forth? They were largely coming from integrating momentum up to infinity. Okay? Or if you were integrating length scales, then the analogous limits would be something like that, where this is the low energy to high energy, but this is the large length scale to the low length scale. And this is where you would encounter your divergences if you're integrating length scale. Okay? However, string theory has a fundamental length scale that's non-zero. We think of a string theory as this string, and then I can take a microscope and I can look at a piece of the string, but a piece of the string doesn't make any sense. The length of a string is the fundamental limit on scales. You cannot, it doesn't make any sense to try and look at something smaller than a string. In fact, there's a duality in string theory which tells you that if you try and probe something at a length scale smaller than the string scale, the answer is exactly what you would get if you probed it at a larger scale. Okay? So, my point is just that string theory has built in a cutoff length scale. And you could put a cutoff length scale into any theory. Like you could put a cutoff length scale into quantum gravity, treating general relativity as a perturbative quantum field theory. But that length scale is going to violate the symmetries. This length scale does not mess with the symmetries attributed to string theory. string theory comes with SUSY. I'm just going to leave that there. No, I'm just kidding. Okay, so with SUSY, first of all, supersymmetry is a natural ingredient of string theory. It's not something you have to dole into it. It's actually just a natural ingredient. But one of the beautiful things about supersymmetry is the following. If we take the standard model and we consider the couplings, then what we find is, remember, all of the couplings run with energy or with length scale. What we find is that among the three couplings, there is a point at which they intersect, but these intersections are at different energies. The lowest intersection is the electroweak symmetry point. Okay, this is the energy scale associated with electroweak symmetry breaking. This is without SUSY. However, if we look at the running of the couplings in the standard model with SUSY, then what we find is the following. All three of the couplings of the standard model actually unite at a single energy level. Okay? Which is clearly much more motivating to the idea of grand unification. That is, that all of the standard model forces actually come from a single gauge force, which has been throughout history spontaneously broken into the different factors that give us the standard model. We talked about electroweak symmetry breaking, but we didn't even think about whether QCD could be unified with the electroweak and the electromagnetic interactions. Okay? Not having SUSY in your theory, it's kind of speculative about, what energy scale that might happen, if it would happen. But with SUSY, these exactly overlap at the same energy scale. All right? So the fact that string theory comes with SUSY is really good. But here's something else cool. Remember how I said string theory just takes point particles and replaces them with strings? It's not trying to quantize gravity, but quantum gravity pops out of it. Well, you might ask, what about the other interactions? What about the strong interaction? Or what about the standard model? Is that a part of string theory? And it turns out that it does. String theory comes with some gauge symmetries. These can be rather large. For example, string theory can come with a gauge symmetry of SO32, or it can come with a gauge symmetry of E8 cross E8. These are the exceptional groups. Okay? In either case, the groups in question have 496 generators, which means that there's plenty of symmetry that can be broken down to give rise to the 12 generators of the standard model. 8 QCD generators, 3 weak interaction generators, and 1 QED generator. All right? So string theory, it's just this assumption that point particles get replaced by strings, but it comes with all of these lovely ingredients, and more, of course, things that people pose as problems. For example, extra dimensions. People hate extra dimensions because they say we only live in 4, but then I'm like, well, fuck you. Have you looked that close to the space-time? Do you really know? We could have a millimeter-sized dimension and you just wouldn't know. Or they could be much smaller. But it turns out that the extra dimensions predicted by string theory give us even more richness. All right? And, of course, string theory, should you ever choose to study it, requires both an intimate knowledge of general relativity and an intimate knowledge of particle physics, circular quantum field theory, integrated together into a single theory. That's it. We're done. And you're silent.
Question, with supersymmetry,
Yeah.
when the weak electric couplings meet at electroweak unification, don't they then run with a single coupling up to higher energy scales?
Yes. Well, actually, I want to do this. Yeah, so beyond the electroweak scale, you could have another shift. No. Okay, so how did this happen? Gabriel? How did this happen?
Higgs mechanism?
Yeah, how does this happen?
Well, maybe the Higgs potential is two humps.
Possibly. This is a much more beautiful picture. Now you might argue, wait a minute, in this picture, if we know that electroweak symmetry breaking is happening, doesn't this mean that the strong interactions have to merge with them at the same point? But what you have to realize is that there's the effects of supersymmetry which come in here. Okay? And so there's a scale beyond which supersymmetry has to play a role. And so our prediction of electroweak symmetry breaking on its own might actually be in hand with the QCD unified theory symmetry breaking once you take into account the supersymmetric effects, which we can't do, confidently yet. Trust me, the scale of which supersymmetry breaking is expected to occur is around the electroweak symmetry breaking scale. We just haven't seen it yet. Because the electroweak symmetry breaking scale, which is very close to the Higgs scale, is actually the largest energy scales we've been able to encounter. If we go well beyond that, then we can actually honestly say, do they get unified with QCD or not? But at this point, we can't do that. Other questions?
How close are we to those energy scales that would show predictions from Susie?
Well, no. That's what I'm saying. We're at those scales. I mean, we've expected to see the impacts of supersymmetry in recent experiments. Of course, we haven't. Okay, but there's many different variations on supersymmetry. There's how much supersymmetry you have, exactly how supersymmetry is broken, because supersymmetry itself is a spontaneously broken symmetry. Supersymmetry predicts the existence of the selectron, which is the supersymmetric partner to an electron, which has the same mass as an electron. Well, clearly we don't see selectrons out there. So there's an energy breaking scale, or there's a supersymmetry breaking scale which gives the selectron a mass which is much larger than the electron, and so we can't even create selectrons and all of the other superpartners because their masses are so large. But what energy scale that takes place at, we don't know. I mean, we expected, roughly based on this argument, that it should be around the electroweak symmetry breaking scale. We've gotten to the electroweak symmetry breaking scale in terms of our energy scales, but we haven't seen it there, so we know it's got to be a little bit larger. But it might just be a little bit larger and not a lot larger, or maybe supersymmetry doesn't exist, who knows? I mean, it would be amazing. Supersymmetry also addresses a lot of other issues in addition to this. Other questions? Okay, you know where we all got to go? We got to go to Physics Fest. Hopefully you're going to go. But I have to get... Yeah, I got to go. I got to get over to Physics Fest now because I got to do some presentations. So hopefully I'll see you there. But otherwise, it's been a wonderful semester. Sorry we had to go to my house. But, shit kind of sucks sometimes. All right, bye, everybody. Yeah, good. Thank you.
Bye.
All right, bye-bye, everybody.